And after the next talk, we will take a break. All right. All right. So you got something new in this part of the talk? Was I communicating clearly? You could get some ideas. That's wonderful. That's wonderful. I'm very happy. Some of the questions were on the dot. On the dot. Your question was good. And have you read my works earlier? No. Well, then that's very interesting. That's very interesting. Thank you so much. So I'll go to the next slide. Then here. It is genuine. All right. Yeah. All right. So the next talk is about drug metabolism. Drugs are $1 trillion industry, and xenobiotics are non-natural molecules that get into your system. Can anybody give me an example of a xenobiotic? Yeah, DDT. Talk to me. Talk to me. Yeah, basically all non-natural molecules, which man-made, you can call them. So these are all published in also decent journals. All right, and they have decent citations. Okay, so and we are going to talk about biological ET and those responses are all in this. So this is going to be a little more packed than the earlier one. Is anybody working along these areas here? Anybody? Yeah, anybody? No? No? Okay, so let's go. So we did chloroperoxidase in the first part. Now the next part, it's a one protein system. Now we are going to the next reaction system, which is a little more complex. It is the drug metabolizing liver microsomal cytochrome P450s. I'll call them cytochrome P450s. I'll call them CYPs. Okay, CYPs. In short. Okay, so they're pretty similar. Both of them have the heme isolate. Both of them can't do the same reactions. But then there are some differences. One is fungal extracellular, highly glycosylated. This is microsomal, this membrane bound. We are coming to membrane bound enzyme reaction systems. Very important, very important. This has got a co-protein, a flavoenzyme reductase, and another protein called cytochrome B5. So there are some similarities, there are some small differences. That is, some other proteins are required for activity, and while this is a polar, a hydrophilic enzyme, this is a hydrophobic enzyme. All right, that is the difference. Okay, but then both are same. So what are the components of the reaction mixture here? Here the reaction mixture is NADPH, flavoenzyme reductase, cytochrome P450, molecular oxygen. All right, and these are the unique reactions that it does: epoxidation, hydroxylation, NS oxidations, dealkylations, carbon-carbon bond cleavage. So basically, here cytochrome B5 is this. Now, all these are hydrophobic proteins. They're all embedded in your liver endoplasmic reticulum. The liver is reddish brown because there's a high amount of these two proteins in that. All right, and liver is the sentinel of your body. Whatever you eat, theoretically it is not in your body yet. It has to go through the hepatoportal system, get cleared. All right, you can go into the body like that. So at that time, those molecules which are not natural, you eat an aspirin tablet. If you eat 10 aspirin tablets, they don't go out of your body. They build within your body. Start building, you will lose your integrity. You will not be human beings anymore. You become slowly aspirin, right? So you don't want that. You want your body to throw out metabolites, those molecules as metabolites. How do they do? Now they attack these molecules, insert oxygen, so they get hydroxylated or they get broken down, and then the water washes it out through the kidneys. That's the logic, right? When you eat your food, you have carbohydrates, proteases, lipases, the major molecule, polymeric molecules that are broken down the classical enzymes. All right, but here these have no topography. Xenobiotics. How does the molecule, how does the body know? So, for example, immune system, you know when the antigen presents itself as an epitope or all like the thing binds and then the memory cells develop and all that. That is there. But one tablet of something non-steroidal anti-inflammatory drug, some statins, sartans, so many different classes of molecules for this, that. How do you differentiate? So there is clearly one region where mosaics can come in. I want to just give you a fair insight on some specific aspects of cytochrome P450. They are basically heme thiolate, and then they are natively Fe3 plus state, low spin predominant over high spin. Okay, so here the cytochrome P450 is called cytochrome P450 because when you reduce it and bind it to carbon monoxide, you get a classical spectrum like this, and that is the way in which it is quantified. How do you know how much cytochrome P450? This is the way it is quantified. So there are two types of binding. We are going to talk about binding based reactions and all that happenings. So here, this is type 2 binding, wherein the iron center directly connects with the ligand. The type 1 binding does not have direct ion connection. So whatever we know on cytochrome P450 is that the proteins that metabolize the majority of the drugs that we consume, that is based on cytochrome P450 CAM protein. It's a protein from Pseudomonas putida, a bacterium that's highly specific to camphor. All right. So it's tightly binds to camphor, and people observe that when it binds to camphor, what happens is this heme undergoes a change in spin. It comes out of the brain, and then its redox potential changes. When its redox potential changes, what they said is this is the switch that is operation. Now, how does this enzyme know when to act, how to act? When the substrate is present in the active site, then it can react. Now here, you have two proteins involved. What is it? One is the cytochrome P450 reductase, one is the cytochrome P450. This is a bit complex. Don't go into the details of this. This is a classical textbook drug metabolism mechanism, wherein the substrate first comes and binds to the cytochrome P450 heme 3 and then changes the redox potential. Then the reductase comes and binds to it. So the mechanism per se is deliberately tetramolecular. That is, this has to bind to the substrate, then reductase must bind, and then oxygen must bind. Multiple things should come one after the other and bind in a deterministic fashion. Now, this is the complex system in which the reactive oxygen species, whether it is superoxide, peroxide, formed, all that requires substrate. All that requires substrate. Without substrate, the oxygen activation occurs at the heme center. The oxygen activation must occur at the heme center because the reductase must pump electrons through protein-protein complexation. How does the electron come to the cytochrome P450's heme center? It comes through protein-protein complexation. I will come to that. My mechanism doesn't have that. I say that reductase takes electron from NADPH, gets reduced, activates oxygen, making superoxide. Superoxide is used by cytochrome P450 to hydroxylate. That's it. Simple. This is the reaction mechanism. Here, there is crosstalk between these two proteins using diffusible reactive species. This makes superoxide. This generates maybe hydroxyl radical or some other reactive species, and then that can react with the substrate to give the hydroxylated product. So now I am putting you another image to show you what. Here, substrate comes and binds, low spin to high spin conversion. Reductase takes electron from NADPH, and then there is a protein-protein complexation. Then intermolecular electron pumping transfer. All right. So then the oxygen rebound mechanism at the heme center. This is what happens. And the cytochrome B5 works as an electron relay between these proteins. So in my theory, cytochrome P450 just uses the ROS generated by this to catalyze. In my theory, cytochrome B5 equilibrates with their orbits. So completely different theory. In the earlier mechanism, it's not going forward. So in the
just awesome.
Yeah, in the if you move your head from there, at least they can see that. I think that is projected, no? Or only that is going. Okay. Stuck again.
No, it's good.
Right?
It's
okay. Good. So now you see in the earlier theory, the oxygen activation occurs at the heme center. In my theory, the oxygen activation occurs at the flavin. It's a completely different theory. And then here there is intermolecular electron transfer pumping and all that. Here nothing like that. All right. So that's what it is. Another representation, that is substrate comes, binds, the electron transfer process gets switched on by substrate binding. It is a topological identification of the substrate that switches on. This is a very important question. Somebody asked how that controlled by substrate. That here it is by substrate topology identification. In my theory, it is by the presence of substrate. Electron sink thermodynamic pull. That is what the control is here. The thermodynamic switch is CPR based activation of electron push, substrate required in the last step only. So that is the mechanism. It doesn't require protein-protein complexation. So yeah, with respect to the active site, what happens is the substrate comes and binds here, then the substrate gets transported, and then there is oxygen rebound, and then the substrate produces the hydroxylate that gets converted to the hydroxylated product. So substrate binds to in bucket, compound forms, then substrate is at bonding distance to FeO, dissociation of the product. That is the classical mechanism. My theory, the Murburn model, is a completely different theory. ROS is produced, and then the ROS can get stabilized, and then it can come out, and the xenobiotic can be present anywhere nearby and get converted. So this cytochrome P450 might present the substrate to enhance the probability of the interaction of the ROS with the molecule. What happens otherwise is the ROS gets to interact with another ROS and just finish. The reaction ceases there. All right. Now, how did I experimentally get around to demonstrating this? In classical theory, cytochrome P450 binds to the substrate, then the reductase comes and binds to this bi-molecular complex. Then to this complex, there is this oxygen binding. And then you have peroxide formation. All right. Now, if that were true, you would expect that peroxide formation, you will need substrate. What I checked, once again, if the theory is right, always don't believe textbooks, don't believe research papers. If you are working on that, try to cross-verify existing paradigms. Always. That's very important if you're a researcher. Do that. So when I did that, I found temporally the substrate lacking mixture showed higher peroxide in milieu than the substrate containing reactions. Whether in the commercially available reactions or in which I reconstituted on my own with pure system. So it doesn't, the theory, classical theory, it doesn't make sense. Or more, it looks rather that when the ROS is used for the reaction, it looks like that. And there are complicated equilibriums involved. That's what this data says. So that is the reaction substrate, including the substrate, showed lower generally sometimes. So in this reaction, what I did is probe the reaction. It is customary to add SOD. SOD, you know, right? Superoxide dismutase, right? And then catalase. These are supposed to convert superoxide and hydrogen peroxide. So if my theory is right, if I have superoxide, dismutase, and catalase are the ones that are involved, if I add that, then I should not get the product. But in commercially prepared or in the usual enzyme assays, I do add this. Then my theory should not be valid, right? If I say that the reaction proceeds through ROS, if I add SOD and catalase, it should take away the ROS. But then I still get good value. But you see, the amount of NADPH consumed is significantly low. What it does is secondary equilibriums, it does away. So here, if you add horseradish peroxidase, you don't get the hydroxydiclofenac product, but you have an enhanced consumption of NADPH. NADPH is the electron donor. All right, now here we introduce some more controls without cytochrome P450. We just try to see, is this NADPH consumption seen even without the substrate? Yes, it is there. So now what I tried is, ascorbate, right? Vitamin C, it's a raw scavenger, right? You know that, right? So when I put the raw scavenger, the hydrophilic raw scavenger, vitamin C, there is no effect. In fact, you get a slightly higher amount of product. But when you put a fatty acid substitution to the same ascorbate, the product stops. The reaction stops. What does it tell you? It tells you that the ROS produced at the lipid interface is crucial. This will localize itself at the lipid. This will not. So SOD and catalase are soluble phase enzymes. This puppy is hydrophobic. You see the effect. The positioning of the molecule at the membrane is very crucial. That affects the equilibrium. So now next phase of my theory is, can my protein make the product without using reductase based electron pumping and transfer? So I devised a mechanism to stabilize superoxide in DMSO and crown ether solution, and then I just added just cytochrome P450 to superoxide. I get the product, beautiful product, but I also have some side products, but I get very good amount of products. And I did for different substrates, different sips, I get it. So the cytochrome P450 is using the ROS generated by reductase is something that I've shown. And then here another experiment, very beautiful experiment is, I took the cytochrome P450 in a dialysis membrane and separated it from the reductase. A specific product formed by cytosine. Now, there is no reductase here. The reductase is present outside. So clearly, the ROS generated by CPR is being used by the C by P. That's the inference. So here again, you see the reductase can on its own produce ROS. Just NADPH plus reductase, you get ROS. So here it is generating superoxide. Superoxide is dismutating to peroxide. That's what you get here. And then you give it peroxide plus reductase, you get this depletion of peroxide. So in the classical theory, if you go back, I will show you 1 second. In the classical theory, the lot of NADPH redox equivalents that is frequently observed in the reaction system was explained by this compound 1 that is formed here, like in chloroperoxidase compound 1. It was supposed to make water here. If that is true, the peroxide species, if you give, it should lead to water. Nothing like that happens. So that is not the reason. The reason is that reductase works by a radical species formation, which is superoxide. Superoxide and peroxide can interact, and that is why you get a depletion. So here that is what I'm showing. So reductase has got secondary function, and there are complex interactive equilibriums involving ROS in the medium. Here, what I've shown is here that part I've established here. Once again, if you ascorbate substitution of palmitate substitution of ascorbate, if you put, you get effect of radical scavenger. You get that, right? Gone. So here, this is structural evidence. All the cytochrome P50s, there are tens to hundreds of cytochrome P50 in the liver. Isozymes. CYP2C9, 2D6, 2C19, 2E13. These are the isozymes names. They have different topology. You see, different topology. Just like antibodies have different binding surfaces for different. You see, here nature, what it does is produces very many cytochrome P450s with different surface topology. But how is the proximal heme thiolate ligand here very beautifully exposed to the solvent? Why is that? So that the superoxide can come, reduce here, and molecular oxygen can bind from there, or directly come and bind. So the probability of their interaction goes high. So this is a stochastic scheme with which it works. The two proteins, there's no protein-protein interaction and electron transfer. It is mediated via superoxide. So now you're coming to the role of oxygen. Oxygen is working as an electron transfer agent, non-specific electron transfer agent, which does the effective charge separation, right? That's what here you are seeing that. And then what am I showing here? Here is non-steroidal anti-inflammatory drugs like diclofenac, ibuprofen, sartans, amiodarone, statin, fluvastatin, trabectedin, antiviral, ritonavir, the Viagra, sildenafil. All these molecules, they are substrate for CYP2C9. This molecule, this protein molecule. How can you explain all these diverse molecules bind with the same active site? Here I say that neither Fisher nor Postland model can explain the outcomes here. Because if that is the case, if it goes, all these go to active site, then why can't some other molecules go to active site? If these can go, why can't some other molecules? CYP2C9 doesn't metabolize some of the drugs metabolized by CYP2E1. It does not metabolize some metabolized by CYP2D6. They have their broad substrate diversity. They have their broad substrate specificity also. You cannot explain both with this. They say that induced fit can explain. That is, the active site opens up. Then why doesn't it allow some molecule? Why does it metabolize? Only some. Now here is how I explain it with the Murburn model. This is CYP3A4. It metabolizes 80% of the drugs that you consume. Very, very important enzyme. All right, pharmacologically. Now you see the protein structure. This is the heme. There is a channel. There's a cavity, large cavity over it, and the channel connects outside like this. The topography is something like this. So the drug molecules cannot access directly inside. What this does is, so it can get reduced, the ion can get reduced by superoxide like this, and the oxygen can come there, or the oxygen can diffuse like that and come and get stabilized here, and then it can make hydroxyl radical by modulation further. And then when it comes out, this is a hydrophobic area, completely hydrophobic amino acids, wherein this radical will be more stable. It will be cushioned on off, stabilized like that. And then when it comes out, it finds these molecules. So what it does is it enhances the probability that the diffusible reactive species can find the targets. And it also explains how diverse workers have argued that this is the species, that is the species. So depending upon the different DRAW species stabilized, you can get different activity. So the phenomenology is better explained when you dock a molecule like trabectedin onto the cytochrome P450. You get beautifully, it docks here, and the aperture is here molecule. When the ROS comes out, so the drug, the various metabolized molecules metabolized. This is the cavity, this cavity. Here it is docking. So it beautifully agrees with the theory that I have proposed. Now, how does it further explain? Now, this cytochrome P450 and reductase, they were supposed to partner via the classical scheme through protein-protein interaction, through the N-term curve. This Nandita Madhavan and I, we had collaborated on this. This was, oh no, so this is Andrew Lane, sorry. Nandita and I collaborated on another thing. So the theories that were prevalent are anchoring. It helps this N-term portion. What is the role of the N-term portion? They found that the reductase's N-term portion, when it is broken, the reaction is critically inhibited. So what they said is that this is an active part of the active site. Is a part of the active site. Now they reductase and CYP, they interact using the N-term. That was a classical hypothesis. I showed they made various preparations of CPR and I carried out the reaction. And then we see that even in the broken reductase, employing cytochrome B5 alleviates the outcomes. It alters the outcomes or alleviates the outcomes. And also the substrate, when you take the different level of substrate, see here, here it is partial broken. Here, when the substrate is at a lower concentration, here you have almost same level, even though it is broken. Here also, when the substrate is high. So it is not necessarily a binding based effect. I showed that the N term has got lysine in it. Lysine residue. What it does is it modulates the ROS, catalyzes superoxide to peroxide, and then if it becomes peroxide, it's no longer useful. So that is what we want to have, the one electron equilibrium. Same thing in substrate. See, these kinds of, when you increase the substrate concentration after a particular time, you might get lowering in rate. What they classical Michaelis-Menten interpretation was that when you have higher substrate concentration, the first molecule goes into the active site and the second molecule comes and kind of stops the dissociation of the first molecule. So this is the active site binding based interpretation of these data. What I said is, now you have low, higher, the intermediate is one electron active. Then if it is too much, it can further react with the substrate and there is secondary reactions. This is what the same interpretation from chloroperoxidase is being applied in the liver microsomal system. Here, the curious case of benzbromone was my paper title in class 1. You remember the movie, The Curious Case of Benjamin Button? Yeah. So, you know, you want to publish a cool paper, you do such kind of stunts, editors like that. So that's some kind of message that I want to give you. You know English, pull around a bit, give a catchy title. You can get it. So the point is that I was working on this and my PI said that this is specific inhibitor for the active site of CYP2C9. I showed no. This inhibits all, practically everything. So I systematically studied after coming back to India. Nandita made the substituents, the different derivatives of these molecules, analogs, and we probed the mechanism. And we found that it's a very curious thing, you know. The more dilute it is, its inhibition power goes up and up. So that's what I've shown the data here. You see here, the lower concentration, the inhibition constant goes down and down. So how is that? So that part would say that it is because of the interpretation that it is going through a radical mechanism. That's all. And here is how I've shown. Once again, the vitamin C and here you see vitamin C. This is ascorbate, right? Now vitamin E is tocopherol. You know that, right? It has got this structure with the fatty acid chain. Vitamin C is soluble. Soluble. It has got this structure, but you can substitute with the fatty acid. So you see the effect here. Vitamin E at lower concentration, you have lipophilic. So basically what you need is at high concentration, you have effect with both. But at lower concentration, you have critical inhibition with the hydrophobic. When it gets positioned in the lipid, you can get with benzbromarone. Benzbromarone is also the same thing. See, you see, this benzbromarone has this moiety, right? This kind of moiety. So what it does is, this is a interfacial raw scavenger. It positions at the interface, and it does that. Nitrophenol, all that we will come across in the respiratory system. These have similar molecular structures. They are similar interfacial radical scavengers. So all these diverse molecules. Oh, it's yeah,
You're trying to turn it off? Or?
Okay. Okay. I thought, okay.
No.
You will.
Yeah.
Okay. So arguments in perspective. So now you have the classical mechanism versus my mechanism. You understood the Murburn model versus the classical mechanism. The substrate binding to CYP. You need the substrate to be bound to the CYP. It must stick with the CYP for the entire catalytic cycle. All the different substrate molecules. How can you explain that? Then the classical mechanics, they say, kinetic isotope effects. There's something called kinetic isotope effects. You substitute the molecule with D atoms, and you see the difference in the ratio of the rates, D versus H, and you see. And then for explaining that, the classical school said that the molecule rotates freely. Only then the observations can be explained. But then their mechanism requires the substrate to be bound also. How can that be? It can either be bound or it can rotate. If it rotates, it's not bound. So say it chooses mutually exclusive options. So then the classical explanation says that the substrate, when it hydroxylates, it detaches from the active site because it loses affinity. In that case, how do you explain the secondary oxidations? The same substrate after hydroxylation, it can go to aldehyde, it can go to acid formation. How can you explain further oxidation? So the new school can explain the stability of thiolate, the oxygen species binding to CYP, the electron transfer. This is a very important thing. One reductase at very low concentration. Reductase is distributed at very low concentration, and it is unique. Hundreds of CYPs at very high concentration. You cannot expect the reductase to be running around catering to the needs of hundreds of CYPs that are located on the membrane. They are not mobile. So redox potential, this cytochrome P50 has got minus 300 like that redox potential. The reductase has minus 250. How can you explain? It cannot give the electron. Protein pumping. It cannot. Then it requires conservation of electron tunneling machinery by the Marcus mechanism. If you involve oxidants, diffusive reactive species, it doesn't. So one reductase, how can it be so promiscuous with respect to all the CYPs? Very simple. It is the reductase producing superoxide which is serving the electrons to the CYP. lots of electron equivalents. It cannot be by compound one forming water. It has to be by the newly observed explanation of reductase mediating the peroxide dismutation. So you have a mechanism here. One mechanism goes sequential, one after the other, highly fastidious, and then multimolecular. One molecule binds to another molecule, when there is no logic for affinity between this. There is non-inducibility. The substrates are not able to induce the CYPs. There are some substrates that can induce, but the vast majority of drugs do not induce the CYPs that metabolize them. There is no connectivity, genetic connectivity. There is no genetic connectivity. So then protein structures, all the diversity of structures is a very simple strategy. Have a lot of CYPs of different topography, then it binds somewhere, it gets converted. All that it does is enhance the probability. So protein structures, distribution, mutation studies, Paul Hollenberg's data of surface residues getting, you change some surface residues and it changes the specificity and selectivity and all that of the protein. How can you explain that? This new theory can. So evolutionary mandate. So now you understand how evolution deals with the xenobiotics. It just burns them at the membrane interface. It's just burning, right? That's why now you are understanding what Murburn is, right? Confined burning. At a small place, we are using a burning strategy. It's not a specified location, binding, just burn it. That's it. So what is the relevance? When a drug comes into the market, it goes through a 10 to 15 year cycle where lead drugs are optimized and all that. And now the NIH project that I used to work on, my PI wanted me to minimize the reactive oxygen species because reactive oxygen species are considered bad. I said, if you take out reactive oxygen species from the milieu, you will not have reactions. You will not have drug metabolism. Fundamental. And you know what happened? I was fired. Not in one lab, in 2 labs. I refused to recant. I came back to India. I set up my lab. And I proved it. If you think something is true, never compromise. It's not what a scientist does. Scientist stands up for what. Then the drug became. Some drugs activate, the same drugs inhibit concentration dependent effect. You can get it in the Murburn model. Because it's the interactive equilibrium. Equilibriums depend upon, paradox equilibriums depend upon electron donation, giving, taking, all that depends upon concentration. Very clear. So, biological electron transfer. I will quickly go over this. Here it is. Now, that is the system of cytochrome P450, reductase, and cytochrome B5. So after seeing that, what I did is some in vitro control experiments. I took reductase ability to reduce cytochrome C. And I checked that cyanide can also affect this, and copper can also affect this. If the electrons, these were supposed to be coming together and binding like that, and specifically, how can small amounts of cyanide and copper, both positive and negatively charged ions, affect the kinetics of electron transfer? Right? And then once again, the vitamin C, vitamin E, and the fatty acid substitution. I see when here cytochrome C is the acceptor. In that, both were in the hydrophobic phase. Here you see the hydrophobic ones practically have no effect, whereas the hydrophilic moieties, because cytochrome C is a soluble electron receiver, you see critically affecting. So here, so partitioning where the electron is, where the product is, all that determines the outcome. Now you see what are the specificity, selectivity criterion. Slowly I have shown here. Did you understand that? Did you understand how these data relate to that? Yeah. Here, same thing. You know, Prolox, the concentration-based effect and the substitution of Here I have shown how protein-protein complexations by the introduction of another protein without cytochrome B5 is present in the lipid phase, in that how the interactive competing equilibriums can affect electron transfer rates. This kind of reactions, when you do, they are so beautiful. Error margins are so low. You see this? So low electron transfer. And you see the rates calculations are so efficient, and they are occurring via diffusible radical species. So the perception that they are chaotic, they are not specific, are all not necessarily based on experimental thing, but it is possible. But when you see, the data is quite reproducible. And here also, without protein-protein complexation, I put cytochrome C outside, reductase inside, I still get here also electron. Not just the substrate formation, here also electron. So in biology, you need not have protein-protein complexation based electron transfer. Electron transfer is mediated by a diffusible reactive species. That's what I'm showing. So here, and that I tried the oxidase peroxidase using peroxide as a activator, using guaiacol as a substrate. Cytochrome C, small amount of cytochrome C I added, picomolar to micromolar. You see how they change at pH, different pH. So it cannot be at this range. The HRP is at nanomolar and the cytochrome C is at sub-nanomolar. So binding based effects is practically zero. I get catalytic activity. And then the activity and inhibition also depends on substrate level. Which substrate you use. So it is the interactive equilibrium, not binding based outcomes. Very clearly demonstrated. Oh, this is wonderful. You see, if it is here, what I've shown is cyanide. You see here, you take 1 millimolar ABTS or 1.2 millimolar ABTS. How many of you have done dose response curves? This, if you have done, you determine IC50. You see, 1 millimolar ABTS molecule that is substrate excluded by the active site. You get same practically same IC 194, 193. Now you see in the pyrogalol, you get at pH 5 0.2 millimolar for you get 44, whereas for 2 millimolar you get 10 micromolar. How is that possible? Here you have more amount of substrate. You use more. How I get much less amount of cyanide required to inhibit. How is that possible? Theoretically, the classical example cannot, classical paradigm to see things cannot. But if you see the data plots, they look active site type. It is not. So basically, all these electron transfers and the inhibitions by cyanide are not occurring at the active site. So here, the effect of cyanide is heme enzymes. So the binding of cyanide to heme or binding of azide to heme was studied, and this was supported some other data by other groups also. The people thought that this is once again a very important concept that I want you to be very familiar, and when you take home this message, it should be very clear. When you characterize a protein's interaction with a substrate or a molecule or a ligand in the lab using spectroscopy technique, you might have higher enzyme active sites concentration. And the ligand, you see here, the bovine micrococcus cat taken at 7 micromolar or 70 micromolar, 920 times and 82 times cyanide for saturation for 7 and 70 micromolar. So you have more amount of enzyme, you will have less amount of cyanide for binding. Do you understand what I'm trying to say? You have more active site, the greater the probability that the ligand can bind. Dilute, lesser. So, but the classical theory states that these are equilibrium and you should not have any effect, such effect. This is experimental work. So So type 2 binding cannot. This was the data thermodynamic pull that I was talking about in the last talk. You see here, I take two heme enzymes and they are supposed to dismutate peroxide. Peroxide can be depleted. So I give a 200 micromolar starting, and after some time, no depletion. But then an active site excluded substrate that can undergo a 1 electron reaction comes into the milieu and peroxide gets depleted. Same in the HR. In the HRP, the effect is even more pronounced. This cannot be explained by the classic. Did you understand the importance? Here is the thermodynamic one. Here, how does the control? The mere presence of a substrate activates the reaction. Did you understand the beauty of it? Did you understand the beauty of it? This substrate is not identified by the enzyme. The substrate presents itself as an electron sink. It's a physical concept. It's a thermodynamic concept. So the presence of the substrate automatically pulls the electron from the peroxide to the. So life evolved with these physical controls also, not just binding based control. This is a classical, beautiful example of Murburn. So once again, the control aspects is what I showed here. The equilibriums involving the components here can give very beautiful, striking outcomes that cannot be explained by standing paradigms, but it can be explained by the Murburn model. That is, so the paradigm shift here is oxygen is utilized as diffusible reactive oxygen species in routine metabolism. Xenobiotic metabolism, if you want to explain it with cytochrome P450, you have to invoke superoxide production. Without that, I have shown conclusively that the system doesn't work. The structures of the CIPs are explained. The distribution of the proteins are explained. The evolutionary mandate is explained. Everything is beautifully explained. All right. And then such processes can give hormetic dose responses. Hormetic is what I said. Lower, it can give lower concentration can give an effect, whereas the higher concentration need not. And then presence of substrate could induce a thermodynamic pull. All right. So here I would like to acknowledge Abhinav Parashar, Daniel, Andrew, Gideon, and Sudeep Makai. Yeah. So this is the end of the first session, wherein I demonstrated through two simple enzyme systems. First one was a one enzyme system with 1 or 2 or 3 molecules that it could interact. Second was a 2 or 3 protein system which can interact with 3 or 4 molecules. What is going to come up is a bevy of protein molecules with a bevy of interacting. Massive things. Respiratory system, photosynthesis. Respiration and photosynthesis are the two fundamental processes on which life is dependent on planet Earth. Yes or no? All living beings respire, right? All living beings, they have to respire. Cells have to respire. And then life, as we know on planet Earth, sustains because the oxygen that we breathe, we get it from there. The carbon-centered biomolecules that we use, the original source is from photosynthesis. So, using these two fundamental systems, I next went to the more complex system. Now, if you play Kho-Kho Kabaddi, right, you use the dodging, the speed, same thing. But nobody really recognizes you if you play Kho-Kho and Kabaddi, right? You need to play soccer, football. You need to play in the leagues. So next part of it is the league. Major game changers. But of course, this is drug metabolism is in itself a $1 trillion industry, right? Yeah, it's a $1 trillion industry. It's still, the textbooks haven't changed. I presented this work in 2006. I have the recording with Low Layer. He arranged. They say you try, don't shoot for the Nobel. You try to see if you can publish the book in the next 15 years. That's what they say. I published it in 10 years. Steve Sliger's lab. You know Steve Sliger, right? Beckman's professor in Champaign. Yeah. So I'm putting it in on record now, deliberately. He should see it because I sent him an invitation. I don't think he registered. And it's his free choice. But then when you know that something doesn't work like that, and when you know and still sit on it, and then teach your younger generations the wrong concept, I think it's a mistake. The fundamental thing that I want to change from now on is this thing should change. Textbooks should change. And then consequently, of course, the drug metabolism industry optimization methods, that should change. And the respiration, if the way we oxygen changes, what changes? Can you imagine? Everything changes. Everything changes. Cancer research changes, neuroscience research changes, everything changes. Now you say reactive oxygen species are bad. You try to minimize, you try to interpret your data completely wrong. Completely goes off.
It is the accumulation of reactive oxygen species which becomes
See, everything has a contextual spatial rules. They say in Malayalam, Amidamayal Amradam. You know, too much, everything also becomes bad. So in this part, does anybody have questions? The audience or
I'll ask.
Yeah.
You can continue.
Yeah. Identify yourself, please. Okay.
So said it is more it's more of reactive oxygen may not be bad. But how do we control it? Because there are also these various radical scavengers enzymes that are present, but those are much lesser than the other enzymes. So if there is a lot of these radicals, then how do we control it?
That's very good, Sharad.
Repeat,
It's a very
please
good
repeat.
question. Yeah.
The alcohol to aldehyde and then acids. But there are also specific enzymes like so then
How do we
even in so many proteins and just to if one can do everything, it could have many copies of it.
question? Now Charulata asked. Now she says, if cytochrome P50s can oxidize in a degenerate, in a stochastic manner, without specificity, it can oxidize everything. Why do we need specific oxidases? That's one part of your question. And then how do we regulate the interactive realm of the overall so many oxidizing enzymes and all? Very good question. Now, honestly, you want me to answer? I don't know. We are at the tip of the iceberg now. We need to understand this. See, our approach is that genes gives RNA. RNA is the central dogma, right? Proteins control everything beautifully, detects everything, concentration, converts everything, and hanky donkey glory, whatever, donkey glory, whatever, hunky dory, whatever. Everything is chocolate, peachy, nice. But then the cell is a mixture, cauldron of molecules. There are random reactions. There are random oxidizing reactions. That's what my pitch is. So my pitch is, let's try to address this whole thing from a fresh perspective, rather than imagining that only deterministic reactions mediated at the active site contribute. Let's see the larger picture. Include all these reactions also into the scheme and try to understand from a fresh perspective, not seeing it as only oxidative stress, but also as an essential component of the redox machinery. Do you understand what I just said? I don't know how exactly it is controlled. I have no clue. And then No, I didn't say that. Charlata, what I said is, I'll come to it. I'll give you a chance to speak. The point is to see ROS or reactive oxygen species as bad as is current. Generally, the major scene is like that. I say that has to change. Okay, without ROS, there is no life. Period. Oxygen is needed to make ROS. That is the fundamental paradigm. There is no way you can escape this paradigm. Oxygen is not needed to make water at complex 4, as is currently believed. Oxygen is needed to make superoxide, hydroxyl radical, peroxide, all these, and singlet oxygen, all that is what is happening. That's what Murburn is happening, which is why you die also. Do you understand? Once you are burning, you have to use the oxygen like that. It's a predicament. You can only continue viably for a certain time. Afterwards, the collateral damage will set in. You cannot escape that predicament. That's the curse and the boon that is associated with oxygen. Now, when you see the ramification of this work, how does this? I will build the system. I will go into the energetics. I will go into the electrophysiology, and then you will see how the cell works as a whole. The aspect of the question that you said now, no, how does the control come in? There is a control by thermodynamic pull and all that. There is partitioning. The overall point that I'm saying is evolution has used oxygen to facilitate. What is the aspect here? Oxygen goes to water, right? The ROS are in the middle, right? And then the products, carbon dioxide, gas, void. Water, you can use it to equilibrate. Osmosis can occur by the. There is automation here. You see, osmotic processes you can use. Water is produced. Combustion produces water. Water, here you have more water. Water will go out. It will take the metabolites and go out. So you don't need supervision for all this. So these were the essential components that were inherently present in the physical state. For example, now you suppose if genes are the directors and proteins are the protagonists, the actors, and you have there's a drama of the proteins are the ones that interact with the large variety of biomolecules, right? No, but then there is a stage, the drama stage. You might have lighting. It throws up some effect. What about those components? That was completely overlooked. And oxygen, he was chosen, finally became as the essential elixir of life, only because, why not nitrogen? Why not some other gas? Because oxygen is a diradical. It has got 2 unpaired electrons. And on the way to water, it equilibrates and it creates these radicals which have high reaction ability. And what that does is the other reaction, that is, for example, hydrolysis, energetically favorable. The esterification, energetically not favorable. So it uses the 1 electron way to achieve. So now if you use a mixie to break fruit, to mince fruit, you can get juice and pulp at the bottom. The way to synthesize the fruit is via another way, not inverting the mixie and putting the juice and pulp from the top and expecting the fruit at the bottom. That's what currently is happening. ATPase is considered it goes, makes ATP, breaks ATP. It doesn't happen like that. You cannot, it doesn't happen. There is nothing in the world that goes like that. Right? I will come to that. That's the next part. Don't miss it. Please bear with me. I'll be very hypercritical about it. I'll tell you. Yeah.
So here, as you can see, that this reactive species, the question of oxygen is very much important. Do you have any comments on the strictly anaerobic systems in bacteria, where oxygen itself is a poison for them?
Oh, lovely.
How does these systems work in that case?
Okay. Oxygen question. Yeah. Sorry. Chinmay asked a question. How can you explain? Now I'm talking about only oxygen now, right? What about the evolution of a system where oxygen is not there, and why is oxygen toxic to those anaerobic systems, right? Very good.
Strictly anaerobic.
Yeah, fine. You do realize that oxygen came into this picture of life scenario of Earth much later, right? First, it was, please, first it was anoxic, and the photosynthesis came much later, and then the Earth got a good share of its oxygen. So now, if you incorporate my theory as the essential paradigm, it is easier to explain the shift from an anoxic to anoxic media, and we can explain why oxygen is toxic to anaerobics, rather than if it is by a specific binding based mechanism. If it is by a mere reactivity model, oxygen, the the windows in which the oxygen works, right? Uh, plus 800 to minus 400. Beyond that, redox potential range, water breaks up into hydrogen and oxygen, right? So you need to work in that window. Now, anaerobes work more into the negative side, and they have a redox window wherein they work. Now, if you have a strong electron acceptor like this, which will go quickly make water, it's all those evolutionary machinery that kind of equilibrated. See, this is where the equilibriums come in. All these reactions, redox reactions, are the ultimate powering. Okay, what is cell? Cell is made of what? Molecules and ions. Yes or no? Now, essentially, there is only one fundamental force that you can deal with. What is the fundamental force that you can deal with? Electromagnetic force. The other two are nuclear forces and then gravitational force. You cannot use it. Electromagnetic force. So the cell has got only one way to deal with electromagnetic force. And what is electromagnetic force? Moving of electrons and moieties. So these molecules and ions, they have to have an interplay among themselves, so that whether it is oxygen or some other molecule, sulfur can also do the job, but it will be slow. Element of sulfur will start to accumulate. Its wastage is slower. That's why oxygen, you see, all the equilibriums work beautifully. When you have a engine, when you this ordinary vehicle, no, you have fuel. You can set it ablaze, and then the gas that expands, you can convert it and then exhaust. All that works fine. How an engine works. Similarly, using oxygen, this effective charge separation, how the thing works is more beautifully explained. So if you see my progress in biophysics and molecular biology text, I've clearly explained how, for example, the enzymes in anaerobic systems, how they can move on to the aerobic systems, why oxygen messes with the anaerobic in detail. Right? So I partly addressed your question. If we have to do a greater justice to that, there is a lot of details that are involved. Perhaps if you refer that textbook, or we can sit after the thing and we can come. Yes. Is there any question?
I just had a comment. So in evolutionary time scale, is it fair to say that the anaerobic systems came first?
Yes.
And that's why they remained simple.
Yes.
And then the aerobic systems.
That's precisely the reason. Because now we could get into multiple systems. We can have a respiratory system. We can have a circulatory system, and all that because of the beauty of this oxygen molecule. Oxygen is a very efficient, effective charge separating molecule. We can move electrons, use our own molecules, and use the laws of physics, enabling us these equilibriums, partitioning, all that working. We can work with ourselves. Yes, yes.
In the docking experiment, you show that you offer multiple site binding of the drug, and that is in a way supporting your hypothesis.
Yes.
But for that, you used any kind of presence of any ions, reactive oxygen species. While
that's a good question. Dr. Pradeep asked me whether in the docking experiment, did I use the simulation of ROS coming out from the active site after binding? No, we didn't have all those sophisticated computing facilities. What we just took is the protein, whatever is known of the 3D. Auto dock, just put blind dock. Where do we get blind docks? Where we get, oh, it supports us good. Chapo paper. No, you see the other option. What is the other option? All these molecules are identified by this Why not that simple? No. Here, it's a very simple explanation. When you have 2-3 different explanations for a phenomenon, there's something called an Occam's razor. Occam's razor comes into play. This is a very simple thing. It explains just now the paper that I argued, putting multiple evolution rationale, why Murburn concept is a primary principle that allowed even the evolution of central dogma that is accepted in Journal of Cellulose. And in that, I am shown how so many systems that lack the components that of the respiratory chain, photosynthetic chain, they also work because there are other ways of getting the things done. Yes.
But I was asking was to identify a protein as a marjan based on such kind of properties. You can take all the protein structures of say.
Yeah. The problem is that's a valid point. The problem is that I have already defined Murburn as something that utilizes, stabilizes, generates, or modulates. These are ROS. So I wanted to get as much get the credits for that, right? But then that's one thing. If we do that, then this part is very difficult to know how. For example, some of the proteins that I will discuss, you will see why we can't do it. It has to come with the context of, can the observations be explained with what we have now? If we cannot, we have to expand our horizons, we have to expand our zeniths. Very simple. You cannot say 1 by 1 by 1 foot, I have 1 square volume, 1 cubic volume, and I have a elephant coming into the room. I make a cone and put it in the 1 by 1 by 1, and then I put one end of the cone into that this thing, and then say the elephant is happily accommodated in the 1 by 1 by. It cannot. That's what is happening. Michaelis method is good. It's a good theory, but not all enzymes abide by that. It's true, but then there is no real argument for diffusible reactive species. Yes, Chimar? Yes. Take a moment. In this case, there should be some lighter moments, right? You have to wear for another 6 lectures. So, yeah. Hope you come. Yeah.
Binding and high concentration binding.
I think they can come here and then stand here and talk with me. That's better, no?
Oh, sure.
Yeah, we keep it there. You just come here and talk.
Next session. For next session, I'll get.
That's an essential thing. You know why I want? I want to give you one message. Scientists should have a very strong ego, and they should be able to face people. It's a very essential thing. Otherwise, you'll be just parroting information that others tell you. And that's not what a scientist is. You need to be challenging. Yeah. And I want you to face people. Don't be shy. Right? Yeah, go ahead.
Sir, you explained about low concentration binding and high concentration binding. And you have you tried to explain about the equilibrium between these two different phenomena. Can you explain that?
Correct. So that's a very important concept. Very important concept. Why? Because the classical enzymology proofs and all were not wrong. But they were obtained using high concentration of the enzyme and their ligands. All right? Or they were obtained with X-ray crystallography. Whereas in the real thing, it is more dynamic, right? In the soluble state. And there are so many ways in which the things that we use to prove something or understand something might go awry in the real scenario. Now, here was a scenario wherein the enzymes are characterized and studied at very high concentrations. At that concentrations, the substrate can access the enzyme active site, and it works quite well like that. But then, the observations that we get in the lab or in reality cannot be explained by us. So for example, I'll give you an analogy. It might not be very appropriate, but it will be my case. All right. For example, and a lion. You can see a lion in a circus ring, right? It jumps through flaming loops, right? Does it earn its livelihood like that in the real forest? No. Point. So if you can use single molecule experiments, sophisticated spectroscopy to show this binds there, this does this, and bring it to the real scenario. See if it can explain. See if that is relevant. Use your all the sophisticated techniques put together. Doesn't beat a man's ability to see. Nah, it doesn't add. It doesn't add. And when you say it like that, that is what I'm saying. Here, I just showed you data wherein I showed theory says this KD concept, it's an equilibrium concept. It should not change. KD should be the same value at you take at 1 micromolar or that point. But the experiment shows me that if I dilute the enzyme, I'm not getting binding. So the point is only when the ligand pressure is high, it kind of diffuses into the active state. Right? I showed you at about 100, when you take in micromolar level enzyme range or nanomolar enzyme range and 100 micromolar peroxide, after a particular time, the peroxide doesn't deplete. So it's not going into the active site. Right? But then you put a substrate that is still outside the active site, there are interactive equilibrium. What happens is the ion center, the redox center there, it need not activate here. There are interactive equilibriums. There are ions conducting, electrons given, taken. The electrons that are originating from the peroxide goes somewhere else via this equilibrium. It need not activate and go and activate at the active site. There are thermodynamic pulls by the one electron equilibrium. For example, you take hydrogen peroxide and sodium hydroxide. You have superoxide formation. Superoxide formation, one electron. How do you explain it? The equilibrium. One electron, two electron equilibriums exist. They have been overlooked largely in the cellular context because of the aesthetic purview that one electron reactions are largely chaotic. Well, then, can we do away with that? That's a reality. We cannot wish away things. We have to accommodate the reality. We cannot wish away the fact that oxygen is a diradical. Given the suitable components, heme and flavins and all that, it can easily go into singlet state. And once it becomes singlet state, the quantum rules of singlet reacting with singlet justified. And then radicals can always interact. Kinetically very facile, 10 to the power 10 per molar per second. Practically diffusion limited reactions. What is stopping it from reacting? So now I'm going to see, after you see the respiration, you'll all agree. I'm sure. When you see what Peter Mitchell got the Nobel for, and when you see my idea, I'm telling you, you will be all fika. I can guarantee you that. Yes. Yes.
Question, can you read?
Yeah. There's a question. Can I just take? Who's it?
Dr. J.
Who's?
Dr. J, this question, can you read?
Dr. J said there are different enzyme specificity hypothesis, lock and key hypothesis, induced fit hypothesis, and substrate strain theory. Actually, these three are telling about all the different possibilities of enzyme substrate binding. Ultimately, which one of these is correct mechanism? Well, thank you for this question. I would say that Birchland introduced the induced fit to accommodate those things which lock and key couldn't official. But still, both of them basically had one side and the two puppies coming together and binding 1:1 complex formation. And they agree with many of the enzymes. They are classical, so many examples, they absolutely explain. But then the examples of reactions, even chloroperoxidase agrees with the Michaelis-Menten for oxygen insertion. But some reactions it doesn't. Right? And when you see the respiratory proteins, That is the question. So I have addressed your question, Dr. J. I hope. Any other question? Yeah.
In that case, continuing to that earlier question about binding up at low concentration, but linear isotope for the absorption is about lower concentration only, but nowhere that.
Well, that's a very good question. See, these things are very important. We are going into that areas of membrane absorption and all that. Do you know one thing? In the cellular biology area, the physicist and the biologist had a long time. It started in early 20th century. It had been going on for almost 100 years. Then there were two schools of thought. One is the membrane pump theory, and one is the association induction hypothesis. Have you heard of this? No. So there was one absorption-based hypothesis by physicists. Now, you know there's something called the transmembrane potential. You know that, right? It's a fundamental feature of cell. Now, the basic mechanistic aspects of electrophysiology, the membrane separation, transmembrane potential, all this, the physicists said that it is by virtue of isotherms and the adsorption-based phenomenon. And the biologist said, no, this is through some pumping. These proteins, they bind. I'm literally sarcastic about some school of thoughts. Please bear with me. And they pump. Just pump. I mean, why? They just pump. So the pumping people want. I'm going to the next one. Peter Mitchell, pumping. Sodium potassium pump, pumping. Our action potential, neuronal conduction, pumping. Just imagine, one stimulus comes, our body decides sodium should go there, potassium should come here, voltage regulates ion movement outside, and then the voltage is regulated by the ion movement also. Did anybody ask why? Did anybody ask why? You should start asking. You should start asking. Anything that doesn't appeal to you, start asking. Why should I subscribe to things that have been given to me in textbooks, that have been given to me by some peers? If it doesn't agree with your basic instinct or basic intuitive appeal, grasp, dare to question. You may be wrong, but you start placing things based on your ideas. You can understand. If I tell you, my dear, if I tell you, okay, there are 4 elephants, okay, found, say, in Mansarovar. Okay, now the 4 elements are found in Mansarovar. Occasionally, when they are found, there's also Maruti sedan that is found. And the elephants have got Kunyagutan, Appugutan, Ramanini name tags in Malayalam. Place Kerala, lots of elephants. And in the Mansarovar, there is hardly any elephant. So there is a Kerala registration, Maruti also found there. 4 elephants, 4 seats in a Maruti car, Kerala registration. So they drove up from Kerala all the way to Mansarovar. Is that a good theory? Is that a good theory? No. How do you know it's not? There is 1-to-1 correlation. There is Kerala involved. There is Malayalam evidence there. How do you know it's not a good theory? Because something doesn't appeal to you, right? What is that doesn't appeal to you? From day-to-day experience, you know that 4 elephants can't fit in a car. Then you know that there is no direct road that the elephants can drive. Then you know that elephants cannot drive. Right? But then you see sometimes in circus, elephants do drive. But then you would say that cannot be this. Similar kind of things. You need to translate. So a simple question that you asked, I'm trying to tell you that physicists who argued for the ion absorption based mechanisms, they were shouted down and shunted out. Gilbert Lynn died a few years back without getting any due recognition. I'm not a membrane pump theory. Then tomorrow there will be a detailed discussion on this. The question that you asked, these are all very fundamental questions. But your textbook will give you only one version. And that's so sad. For a researcher, it's the biggest curse, I tell you. You don't get to, she has published in this area for since 2006. My book, nobody knows. Respiration I've been publishing for the last 5-6 years. Nobody knows. Not nobody knows. They know, but they pretend they don't. How many BSB people here? One. One BSB. One BSB. I wrote to everybody in BSB. What do you think about that? What does it tell you about the scientific world? Whoever has the money, grants, whoever has the authority, power, they'll shepherd their people. Scientists are not sheep. Scientists challenge them. So when you are doing research, don't go by any single doctrine. When you are doing research, fine. So your question was, does it find out? I am open. I am here to discuss a few topics. All right. I am adsorption. Those people talked about adsorption-based kind of phenomena, binding-based phenomena, as one that led to so many other explanations. They were all shouted down, shunted out. And pumping got the accepted. That is the premise for the next talk. I think 11:30 the next session starts. So I think they should get a break, no?
Yeah, let's take a 10-minute break.
Yeah. Okay. Yeah. Have you announced to the people, no?
Yeah. Thank you, people joining online. We'll take a 10-minute break. I'll put a timer on the screen. Thank you.
Yeah, that's good. Am I communicating and am I addressing your question properly?